Welcome back. In this video, I'm going to do the solution to the example at the end of the extreme values section. So just like the example before it, we're asked to find the global extrema, so this means max and min, of this cubic polynomial on this interval. So this -4 to 3 is telling us that -4 is the lowest x value we're considering and 3 is the highest. So it kind of gives us like a left and right cutoff for the graph. So this is my A and this is my B. And we know that the extreme value theorem applies here because this is definitely a continuous function, it's a polynomial, and this interval is closed, meaning it has brackets on both edges. That's the scenario where the extreme value theorem tells us that we're going to actually get answers for both parts of this question. It's not something that you're going to have to consider heavily at the beginning of problems in this class, right? I'll always give you a function that's continuous and an interval that's closed, but it is something I want you to think about as you do these problems, because when you run into these in the real world, you can have some issues when either the function isn't continuous or the interval isn't closed. Okay, so the first thing we want to do, now that we've decided that it fits our theorem, is we want to find the critical values. So I'm going to say CV for critical values, and that's going to be the way that we start a lot of different examples in this section and in several sections in the future. So to find the critical values, I want to compute the derivative of the function. So I'm going to have f prime of x, and I'm just going to do this guy's derivative right in line here. So I'll have 6x squared plus 18x minus 60. Okay, so there are two ways to get a critical value. One way is for the derivative to not exist. So when I say DNE, I mean does not exist. In this case, that just isn't an issue, right? The derivative is a quadratic polynomial. There's nothing weird happening here. So we'll kind of consider it for a second and then say, there's no case that's happening here. And we'll move on to the second scenario, which is where the derivative equals 0. And that's usually where our critical values come from. Every once in a while, though, you have to always check, because every once in a while, this does come into play. So for example, if your derivative had a 1 over x in it, you can't plug in 0 to that derivative, so you would say 0 is one of my critical values. It's rare, but it does happen, so make sure you always consider it before you move on to the second type. Okay, so now I want to set this function equal to 0, 6x squared plus 18x minus 60. So now, this is a little bit intimidating. There's a couple of different ways to solve what we're looking at here. One way is the quadratic formula. So you could do the quadratic formula. Some people, that's kind of their preference, they jump right into it. That also means that you can use a calculator fairly quickly to kind of help you with that computation. This quadratic does factor though, so I'm actually going to do it without the formula. I'm going to just factor it. So I'm going to realize that all three of these coefficients are divisible by 6. So I can take a 6 right out, sort of undistribute it. So I have x squared plus 3x minus 10 in those parentheses, and then I'm going to factor this. This may be a serious throwback for you, so I want to kind of go through this a little bit extra slow. So I want to pick two numbers here that multiply to -10 and add to 3. That's going to be plus 5 minus 2. Here. And again, if you hate that, you could also throw this into the quadratic formula and it would lead you to the same two correct answers. All right, so this quadratic will equal 0 when 6 equals 0, which is never, when x plus 5 equals 0, or when x minus 2 equals 0. So I have two critical values, -5 and 2. So I'm going to kind of identify for myself. I've got two critical values. I got none from over here and 2 from over here. So my next move in the process is to make an XY chart and test things. So the XY chart. So I call it an XY chart, but then what I actually do is X and f of X. There's no special reason I use f of X instead of Y, except for the fact that I'm reminding myself one more time that I'm not plugging numbers into the derivative. I'm not using this anymore. This is gone. I don't need it anymore. I'm plugging into the original f of X from the beginning up here. All right, so why don't we remind ourselves of that one more time. That's 2x cubed plus 9x squared minus 60x. Those numbers will be a little bit annoying, but we'll use a calculator to get past some of it. All right, so what I want to test here are my critical values, along with what we call A and B. These are the edges of the interval, right? Because there may not be something special with the function happening there, but if that's the cutoff point, it could definitely end up being a max or min. So we have -4 to 3. Before I start, I can throw away the -5. I'm going to save myself some trouble and cross this out before I even bother. And it's because -5 is outside of the interval -4 to 3, right? It's too far to the left, whereas 2 really is in that interval. So I'm going to toss this because it's not in the interval I'm concerned with. If it were in, we would keep going with it in the chart. Okay, so now I want to plug 2 into my function. So we'll have 2 times 2 cubed plus 9 times 2 squared minus 60 times 2. And I get -68. Okay. Now we'll go through and put a -4 into the function instead. So I'm actually going to use this same line and put a -4 in that spot. And then here. And here. And I get 256. That's a big Y value. And we'll do this one more time with a 3 instead of the -4. And we get -45. Okay, so these are bigger, grosser numbers, but that's okay, the process will still work. So the lowest of these 3 numbers is this -68. So this is showing me the global minimum. So I'm going to say I have a global min at 2 -68. I could have said that the global min is -68, but since I have its x value right there, I might as well put it in xy form. And then the highest y value is that 256. So I'll say, all right, I have a global max at -4, 256. And that's my final answer. So take away kind of a summary here before we end. What we did was first briefly consider I have a continuous function and a closed interval, which we always will, but it's good to think about. We found critical values by finding the derivative, considering if it has any domain restrictions, which it doesn't, and then otherwise setting it equal to 0. If solving this equal to 0 is something that didn't come back to you really clearly, where the quadratic formula and factoring, neither of them really kind of comfortably came back, that's something that you want to schedule a video chat with me about, or schedule an appointment with one of our tutors, and they can kind of help you recap that part so it doesn't trip you up in the middle. Once we had our critical values, we put them in an XY chart with the endpoints, tossed anything that wasn't actually in the interval, so -5 kind of disappeared, plugged everybody into the original function, lowest Y value wins, highest Y value also wins.